Well, good morning, good afternoon, and good evening, ladies and gentlemen. Today, we are going to be talking about the chemistry of life. So we are moving into our third unit here in biology. We're going to be talking about biochemistry, and today we're going to be giving you a little bit of the introduction to the chemistry inside your body and why it's essential for life. Let's go ahead and dig into this, shall we? So the first thing we're going to talk about today are elements. So what elements are, they are the fundamental forms of matter. Each type has only one type of atom. Now, atoms are the smallest, absolute smallest particles that we can work with. And they cannot be broken down into simpler parts and keep their unique properties. And 92 of these occur naturally on Earth. That's right, we're not talking about your traditional four elements. We're not talking about earth, water, wind, and fire. No, we're talking about something a little bit more complex, which I'm sure you've probably seen in the periodic table, but we'll talk about that later. So if you'd like to, you can go ahead and watch the element song here by clicking on this link down here. It's by, I think they might be giants. It's a nice little introduction to the types of elements you might be seeing. I'm not going to show it because copyright infringement, we don't want any of that. So whether or not you choose to watch it, I will see you on the next slide. So the most common elements in organic molecules can be summarized with the acronym CHNOPS. These stands for C, carbon, H, hydrogen, N, nitrogen, O, oxygen, and also we have trace amounts of phosphorus and sulfur. So those are the most abundant organic molecules. So organic, we're talking about living molecules. These are the most abundant elements inside living creatures. And, we also have some calcium and potassium inside there as well. So, as we can see here, naturally occurring elements inside the human body. The most abundant is carbon, right here. Whereas the most abundant in the Earth's atmosphere would be nitrogen. That's right, oxygen is not the most abundant element inside the atmosphere. So, what are atoms exactly? That's the big question here, or the small question depending on how you look at it. So, atoms are the smallest particles that retain the original properties of an element. And they are made up of subatomic particles. And those particles are, we have protons, which have a positive charge, we have electrons, which have a negative charge, and we have neutrons, which have no charge. So, the atomic number, which is, we have one for each of the 92 elements, including the graded ones we made in the lab, but anyway, there is a unique number for each one, and that is the number of protons or the number of electrons. Meanwhile, if we go ahead and add the total number of protons and the total number of neutrons, that's going to give us the atomic mass. So, protons or electrons gives us the atomic number, and atomic mass is protons plus neutrons. Now, once again, there is a video here that'll show you exactly what an atom looks like, or a nice representative model. So if you want to go ahead and click the video below, you can take a look at that. I'll see you on the next slide when you're finished. So here's a little peek at the periodic table. Now, this is not all the periodic table, mind you, but it just shows you some of the elements that you'll be looking at. So which were the most common in living things again? Which elements? I'll give you a sec to think it over. Just gonna take a little swig of coffee here. Oh yeah. So, remember, CHNOPS. We have carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Those are the most abundant elements in living things. So, isotopes. When we talk about isotopes, we're talking about atoms of an element with different numbers of neutrons. So they have a different mass number or different weight. So for example, Carbon normally has a mass number of 12, and it has 6 protons. So remember, mass number, or atomic mass, equals protons plus neutrons. So if we go ahead and subtract the amount of protons from the atomic mass, that would give us our number of neutrons, which is 6. Now let's say we had carbon 14. So once again, we would take 14 and subtract 6 from it. So if we do that, what would we get? We would have 8 neutrons. So isotopes are just elements that have a different number of neutrons. Simple as that. And remember, your atomic weight, or atomic mass, is the number of protons plus your neutrons. So radioactive isotopes have excess neutrons. Now, when this happens, we mostly get radiation. Radiation is mostly the extra neutrons that shoot outside the nucleus. So the more neutrons we have, the higher the atomic mass, the higher amount of radiation emanating from that atom. So they can act as tracers because they show up on X-rays and radiation detectors. And following these tracers is useful in many areas of biology. So what we have here is, how many of you, well, I'm just talking to kind of like one person right now, I guess, but have you ever had an X-ray where they had you swallow something beforehand? Well, chances are if they had you swallow something beforehand, before you took the X-ray, what you swallowed were radioactive isotopes. What that does is it allows the doctors to go ahead and see soft tissue that normally would not show up in an X-ray. So for example, if you swallow barium, this helps doctors see the large intestine, which would normally not show up on the normal X-ray. So what we have here is we have the small intestine leading into the large intestine, and here we have a picture of someone's thyroid gland. Remember, the thyroid gland is a butterfly-shaped gland right here on either side of your windpipe. So, the more you know. Little fun fact. So, what determines how atoms interact and bond with each other? So the number and arrangement of the electrons in their outer shell is how they determine what will be bonding with what. So atoms are happy and stable when their outer shells are full. So they want their outer shells to have the maximum amount of electrons in them. The first shell can hold 2. The second shell can hold 8. So let's say we have our nucleus of the atom. Then we have our first shell. Then we have our second. So let's say these little yellow dots, let's not go with yellow, it's kind of hard to see. Let's go with red. These little red dots represent the electrons. So in the first shell, we can hold 2. In the second shell, we can hold up to 8. 2, 3, 4, 5, 6, 7, and 8. I'm not gonna lie to you. I do not like drawing with a mouse because it looks like a 4th grader did it. So bonds and molecules, compounds, definitions here. So a bond is a union between electrons of atoms. So that's how we go ahead and combine certain elements. We go ahead and put their electrons and bring them together. So a diatomic molecule would be 2 or more of the same type of atom or element bonded together. So as we can see here, we have H2, N2, or O2. So that means we either have 2 atoms of hydrogen, 2 atoms of nitrogen, or 2 atoms of oxygen bonded together. A compound, on the other hand, is 2 or more different types of atoms or elements bonded together. So here we have H2O, which is hydrogen, 2 molecules of hydrogen, and oxygen, 1 molecule of oxygen. So Diatomic molecule, two of the same. Compound, two different. So the first type of bonding we're going to talk about today is something called ionic bonding. So ionic bonding is an exchange. So one gives and the other accepts the electrons. So an ion is a charged atom. It either lost electrons, which would give it a positive charge, or gained electrons, which would give it a negative charge. But wait. You mean to tell me that if something gains something, it's negative, and if something loses something, it's positive? Well, hang on, let's think about this. So what they're doing is they're losing an electron. So an electron, remember, has a negative charge. So if you get rid of a negative, that makes it positive. And if you gain an electron, that means you have one more negative charge on there, which is why the whole thing would be negative. So if one atom loses electrons, which is positive, and another atom gains these electrons, is negative, the charge difference attracts the two ions to each other. So what that means is we have a positive and a negative. Think magnets. If you have a positive and a negative, slowly the two are going to come together. So here we have a classic example, which is sodium, Na, and chlorine, Cl. So what they do here is you can see that sodium has one extra electron in its outer shell. Now if it got rid of this, it would have 8, making it happy. Meanwhile, chlorine has 7 in its outer shell. It's missing 1. So what's going to happen is the sodium will donate its electron to the chlorine. So now we have 8 in the outer shell of sodium, 8 in the outer shell of chlorine, meaning that both are happy. Yay! However, since sodium lost an electron, that's going to make it positive, and since the chlorine gained an electron, that would make it negative. So the two would come together, positive and negative, forming a bond. So ionic basically means you're making an ion. You're giving one or receiving one. So you're either giving away an electron or receiving an electron. So table salt is the most famous example of an ionic bond. Sodium's outer shell has 1 electron, chlorine's outer shell has 7 electrons. The sodium transfers the electron to the chlorine, forming Na+ and Cl-, and the ions attract and remain together as NaCl. Fun fact. The next type we're going to talk about is covalent bonding. So covalent is when atoms share a pair of electrons to fill the outermost shell. So that means we have a single covalent bond that shares 1 pair of electrons. So single covalent is sharing 1 pair, or 2. A double covalent, we're just doubling the amount. So a double covalent shares 2 pairs of electrons, or 4. A triple covalent shares 3 pairs, so 6. But we're not really going to be moving past, I think, single covalent in this class. So here we have 2 atoms, right? So we have atom number 1, atom number 2. And as you can see here, they are sharing 1 pair of electrons between them. So hydrogen bonding. To understand hydrogen bonds, you first must understand something called polarity. So polar, what comes into mind here? Think the Earth. I'm going to assume you said the North and South poles because, well, I'm a recording and can't really interact. So when a molecule is polar, electrons are not shared equally, meaning that one part of the molecule is more positive and the other part is more negative. So we have a difference in the charge. Now a classic example of this is water, H2O. So as you can see here, the hydrogen has a slightly positive charge, and the oxygen has a slightly negative charge. So to continue talking about hydrogen bonding here, it forms between the more negative atom in one polar molecule and the more positive atom in the other such molecule. So usually in the case of water, the more positive atom is hydrogen. Why? Hydrogen can only take one electron in its outer shell. Meanwhile, this normally forms between hydrogen and either nitrogen, oxygen, or fluorine. In the case of oxygen, oxygen can hold, I believe, up to 8 electrons. So, there are more electrons around the oxygen than the hydrogen, making the hydrogen more positive and the oxygen more negative. So, these form between the hydrogen and either the nitrogen, oxygen, or fluorine. So, as you can see here, our hydrogen, which has a positive charge, is going towards the nitrogen, which has a more negative charge. Remember, positive to negative, holding each other in close proximity. So some other examples of hydrogen bonds, a huge one, now it doesn't really show you this right here, but hydrogen bonds hold together our DNA. Now this is important because we need a relatively weak bond to hold that there, because we need to be able to go ahead and separate our DNA strands to make a copy of it. Now if we had something strong like a covalent bond, it would take a lot more energy to go ahead and reproduce our DNA during mitosis and meiosis, which basically means we would have a lot less energy to do anything else, which isn't good. Now, the most classic example when it comes to hydrogen bonds that you'll have to remember is water. So water is the classic example of hydrogen bonding. So we have a positive side on the hydrogen, negative side on the oxygen, so these two most likely come together like this. Voila! So, water held together with hydrogen bonds. Now we're going to be going a lot more in depth with this in the next slide, or not the next slide, but the next PowerPoint series here. So that just about does it for the introduction to biochemistry, or the chemistry of life. So today, remember, we talked about what chemistry is, why it's important. We talked about the different elements, the most abundant elements or organic elements inside your body, and we also talked about how elements and atoms can bond together. Well, that's just about going to go ahead and do it for today. So thank you for joining us, and until next time, I will see you in the next video. You all keep it classy.